Welcome to CSAI Think Tinkerler. This is part of my System Design Essential series. The goal here is to give you a mental model of system design topics. We're breaking down network partitions and split brain handling today. This is a concept first introduction to help you build your system design foundation quickly. If you want to see a deep dive on the trade-offs or a specific case study, let me know in the comments. No fluff, let's get into the technicals. But before we begin, please hit that like button if you like this video, share this video, and subscribe to help us grow. This series provides high-level architecture view to keep the lesson short and effective. For the full articles and diagram, you can visit our companion website, which is here. So you can go here. This is currently, the link will be in the description, is CSTTL GitHub pages. And you will find some articles here. This is a work in progress. So as and when we keep moving with our article series, you'll find more articles to be listed here. And we'll keep on making the videos as well. Okay, let's go for the network partition and let's design for the disasters. Okay, so what's a network partition? A network partition is when a link fails and your cluster fractures into isolated islands. The nightmare scenario is split brain. Imagine partition island 1 has the original leader, but partition island 2, thinking the leader is dead, promotes the node C to be the new leader. Now you have two kings. If both islands continue to accept rights, their history diverge, leading to a silent data corruption that is often irreconcilable once the network heals. This brings us to the CAP theorem. When a partition occurs, you must choose between consistency or availability. In a CP system, you reject writes when you are uncertain, choosing safety over uptime. In an AP system, you accept write on both sides, risking divergence to keep the system online. A senior insight to remember: CA, which is consistency plus availability without partition tolerance, is a myth. In distributed networking, everything eventually partitions. Our first layer of defense is the math of quorum. To prevent two islands from both thinking they are in charge, we use the formula quorum equals the floor of n divided by 2 plus 1. In a 5-node cluster, quorum is 3. This provides a mathematical guarantee. Two separate partitions can never both achieve quorum simultaneously. There simply aren't enough nodes to group around, ensuring only one side stays authoritative. The engine used to manage this state is usually the Raft consensus algorithm. Nodes exist in three states: leader, follower, or candidate. The leader is the single authority for writes and heartbeats. Followers are passive listeners. If a follower stops hearing heartbeats, it enters the temporary candidate state and requests votes to become the new leader. The state machine ensures the cluster always attempts to converge on a single source of truth. Crucial to Raft is the heartbeat timer. Every follower maintains a random election timeout, typically between 150 milliseconds and 300 milliseconds. Heartbeats from the leader reset this timer. If the timer expires, the follower becomes a candidate. The randomness is the secret sauce. It ensures nodes don't all time out at the exact same moment, which prevents constant multi-way election ties and voting gridlock. Even with Raft, we face the zombie leader vulnerability. A node can pause for seconds or minutes, often due to JVM garbage collection pause. During this time, the rest of the cluster elects a new leader. When the zombie wakes up, it still believes it is the king and may attempt to write to shared state. This creates a silent race condition that can bypass standard software checks. To stop zombies, we use layer 3 defense, storage level fencing tokens. Upon election, the log service issues a monotonically increasing integer. Every write must include this token. The storage layer, be it a database or a file system, maintains the highest token it has ever seen. If a zombie leader shows up with an old token 4 when the storage has already seen token 5, the write is rejected unconditionally. Enforcement moves from the node to the resource. In a shared physical storage environment like a SAN, software logic might not be enough. We use layer 4, STONITH, which stands for shoot the other node in the head. If a node is suspected of being a zombie or behaving erratically, The healthy partition uses out-of-band management, like IPMI power cuts or SNMP switch disabling. This is to forcibly shut everything down. A powered off node cannot corrupt data. It is the ultimate failsafe. But what if you can't afford to go offline? AP systems like Dynamo or Cassandra deliberately remain active during a partition. They abandon strict quorum for writes, allowing both sides to mutate state independently. Here, you trade immediate consistency for 100% uptime. The challenge shifts from prevention to conflict resolution. How do we merge the two different history once the partition heals? There are two main ways to handle the resolution shutdown. Last write wins is the default for Cassandra. It compares timestamps and silently discards the older write. This is fine for social media likes, but unacceptable for financial ledgers. Causal merge, used by Dynamo, tracks node counters via vector clocks. If versions intersect without one dominating the other, both are surfaced to the application for a semantic merge, ensuring no data is lost. When partitions heal, scanning petabytes of data for mismatches is too slow. We use anti-entropy repair powered by Merkle trees. Nodes exchange tree hashes rather than the raw data. By comparing top-level hashes and traverses only the mismatched branches, then the system isolates divergent data ranges in O-Lagan comparison. It is a surgical way to repair a massive dataset with minimal word network overhead. Let's look at the real-world blueprint. etcd and Zookeeper are CP system using Raft or for control planes where consistency is king. Cassandra and DynamoDB are AP system prioritizing write availability. MongoDB is typically CP, using majority write concern to prevent split brain at the replica set level. Choosing the right tool depends entirely on your stance on the CAP Theorem Fork. As an architect, your filter must be defense in depth. Junior engineers think Raft solves everything. Senior engineers build the whole stack because they know every single layer will eventually fail. Math prevents multi-majories. Raft sequences the logic, fencing token guard the storage, and STONITH guards the bare metal. You need all of them to survive a true disaster. To conclude, split brain is not just a bug to be fixed. It is a physical reality of distributed systems that must be managed. When asked about network partition in an interview, don't just name an algorithm. Demonstrate the full architecture of isolation, validation, and recovery. Now, I have a question for you. What's the most difficult data corruption issue you have ever had to clean up after a network partition? Share your war stories in the comments. If this episode helped you, please like, share, subscribe, and click on that notification icon so that you can get notification on all the subsequent videos related to system design. Check out our site for more essential topics. Thanks for watching. Until next time.